closure of a set E. Closure of set E will be given by E union E dash, where E dash are derived set of E, where E dash is equal to A, set of all limit points. We know the definition of limit points. Point which is contained in E, a point which is contained in E have a point other than, like for example, a point P belongs to E, contains other points of E other than P, and also contain points contain points of X which does not belongs to E is called a limit point of E. One theorem that I am explaining related to this is that we have to prove that E closure is closed. We have to prove that E closure is closed. That previously we have seen that E closure is nothing but a constitute of points that is E union DA, alright, DE instead of limit points. Since we know that if a set contains limit point, that implies it is closed, right? We just have to explain E closure is closed. We just have to explain that it has a limit point inside it, and this limit point, we just have to explain the limit point, concept of limit point. That's it. We can prove that prove that E closure is closed. For example, now let X belongs to E closure. All right, so that means X belongs to E union D of E. That means X belongs to either of these. X belongs to E or X belongs to D of E. All right, we can write this. If X belongs to E, since X is arbitrary, means all the points of X is any arbitrary point, and if X belongs to E, then there is nothing to prove. All right, since all the neighborhood of X contained inside E, there is no point of E is a limit point of E. So from this we can get that E is closed. All right, if X does not belongs to E, that implies X belongs to E dash. All right, E dash is nothing but set of all limit points, that is the derived set of E. You can write derived set of E as well. Now if X belongs to E dash, and if you're considering a neighborhood of NRX of E of X inside E, so that means that neighborhood will contain other point that is different from this X that we considering that as Y point which is other than X that belongs to this NRX and is a subset of E. All right, now basically we get that we get by the definition that X, then every neighborhood of X contain a point Y of E other than X, that implies that X is a limit point. Since it's a limit point, we get that E is closed set, right? E closure is a closed set. But one more thing that I want to add here is that we can prove for one more point belonging to this NRX neighborhood. Let, for example, Z. If I consider Z with a radius R dash, which is less than the radius of R of X, and the radius of Y less than the radius of, which is less than the radius of A, then this Z belongs to, we can write NRX. We can say that Z belongs to NR dash of Y. We are just using R dash for the radius of Y, and we know that NR dash belongs to this NR dash, Y belongs to the NRX. That implies NRX. That implies we get that another point of E belongs to another point Z. Sorry, not this Z. This Z. Z belongs to E. By this we can conclude that there are infinitely many points can be present in this NRX if you repeat this process infinitely many times. So hence from that we get that E closure is closed. Alright, the next concept that we have here is next theorem. Wait a minute. We have proof. If we have E equal to E closure, that means we have already proved that E closure is closed. All right. From this we can imply that E is also closed. Right. Now, basically you can write it as E equal to E union E dash, right? From that we get that E equal to E closure. That's it. Further, I just want to add something here. Is since E closure is closed, alright. Since E closure is closed from previous example, and if E is closed, we can say that E is closed. We can say that all the limit points of E is contained in E. All right. All the limit points of E is contained in E. So from there we can say that E dash is a subset of E, and since E closure is a largest closed set of E, we get that E is a subset of E closure. From 1 and 2 we can say that E equal to E closure. From this we can conclude that E is equal to E closure. Alright, this is pretty much simple. Now next concept is that E closure is a subset of F. If here F is closed, we have to prove that E closure is a subset of F, and if F is closed, we know that if F is closed, that means we can write from previous theorem that F limit point of F is contained in F. Alright, is a subset of F, and since E is a subset of F, we get that E is a subset of limit point of f is a subset of f. From this we can imply that, from this we can get that we can get that since f closure is closed, we get that E is closed. See, hence if E is closed, we get that E is equal to E closure. Alright, and this implies that E closure is a subset of closed set F, and which is also closed set. For systematic procedural steps, you can follow your textbook. I'm just giving the brief analogy behind it, and if you want to add, you can add some more concept like that is neighborhood. You can consider neighborhoods of an Rx which contains a point E other than X, so that this neighborhood of X will belong to F. This is how you can prove also. From that we can get that E closure will be the subset of F closure. For example, you can consider a point X belongs to E, that implies X belongs to E closure. Alright, if sorry for the disturbance. Okay, from the E we get this, and since E is a subset of F, we get that E closure is a subset of F closure. Alright, or you can say that, or derived set of E will be set of derived set of F dash, since F is a subset of since E is a subset of F. So this is pretty much some concept related to E closure. And one more thing that I want to add is if we call a set dense when we get the E closure equal to X. Alright, for example, we can consider our rational numbers, set of rational numbers. Alright, is dense in R. Right, if you consider any epsilon neighborhood of neighborhood which belongs to Q, an epsilon Q, we get that X minus epsilon and X plus epsilon, which belongs to Q. Since each epsilon since each rational number, in each between rational number we have infinitely many rational numbers, and from that we can conclude that every number in this epsilon neighborhood is a limit point of Q, or the point of Q. So from there we can say that Q is dense in R. Alright, so from the limit point of Q, from that we get the limit point of Q, the closure of Q will be equal to R. Alright, since limit points of Q are, we know that Q dash, that is irrational numbers, and if it is not a limit point, then this point X, it will be equal to, it will belong to Q. Hence we can say that every neighborhood of Q, Q will belong to Q, or it will be a limit point of Q. Hence we can consider that R is Q is a dense subset of R. Alright, next theorem that we have here is E closure be a non-empty set of real numbers, and which is bounded above by y, that implies y is a supremum of e. We have y is a supremum of e. Hence, then y belongs to e closure, because the limit point of e should be the supremum of e, and y belongs to e closure. Hence we can conclude from here, if e is closed, we know that e will be equal to e closure, and y belongs to e that belongs to y e closure whenever e is closed. That's it. So to prove that, you have to take y, just explaining briefly, y belongs to e closure. That means y belongs to e or either e dash. If y does not belong to e, then that implies y belongs to e closure. Now, considering a neighborhood of y and dou y with a radius dou, it is y minus dou comma y plus dou. Alright, now since there is a point x naught, considering a point x naught belongs to this neighborhood, so we can say that y minus dou is less than x naught is less than y, just considering, and is less than y plus dou. We got an interval over here. From there we get that x naught belongs to this neighborhood and dou y. Whenever we do intersection with e, x naught belongs to and dou y intersection with e. So basically we got that y is some point which is already which belongs to e, closure, which belongs to e closure, and we get that there is another point belongs to this and dou y, that is x naught, which belongs to this e. So we get that y is a limit point of e. For systematic steps, you can review your textbook, follow from your textbook. Alright, and few more concepts that we have here is related to interior points. I'm gonna explain right over here is a few points that are related to interior points. We know that E interior is a point which lies completely inside a E interior. 3 points x1, x2, x3. E will be equal to x1, x2 and x3, for example. Then all the points of E is an interior point. From there we get that E interior is equal to E is equal to E interior, and we know that by the definition E interior is always open. To get that definition, is always open. For example, there is a point x belongs to E interior. That is what I have shown. We shall show that x is an interior point, x belongs to E interior, right? We have to show that this is x belongs to E. There is a neighbor and dou of x is a subset of E, and dou x is a subset of E. There is a point y belongs to this n dou x belongs to E, means there is a n dou dash of y where dou dash is less than, obviously it is less than n dou x, it is less than n dou, which is less than dou basically, So hence we can conclude that this y belongs to, y is a subset of endo x. That implies that is endo dash of y will be subset of endo of x. From this we get that every point of E, or every point which belongs to endo x is an interior point of endo x. From there we get that every point of endo x is a subset of E interior. From there we get that E interior is open. Since endo x is open, we get that E interior is open. All right. And one more concept problem there is E is open. All right, E is open if and only if E equal to E interior. We just have to take 2 points, x and y. Case 1 in this, if x belongs to E interior, we get that E is a subset of E interior. If case 2, if y belongs to E, we get that E interior is a subset of E. From 1 and 2 we get that, from case 1 and case 2 we get that E equal to E interior. For systematic procedural view, you can review your textbook or from wherever you are trying to learn from. In order to belong this x and y to E, we have to consider that E is open. Alright, so whenever, if and only if E is open, we can write this y belongs to E, and we get from that, if E is open, we get that from that E interior is a subset of E. Alright, and if x belongs to E interior, we get that E contained in E interior. All right, so from these two cases we get that E interior is equal to E if and only if E is open. Now E interior is the largest open set containing E. All right, so we know that E this is the next concept theorem is that E interior is the largest open set containing E. This is E. This is sorry. This is not. This is E. This one is E interior. All right. There could be many neighborhoods inside it. All right. So consider another open set which consists of all these neighborhoods of E. So from that we can say that E is a subset of a union of all neighborhoods. All right, union of all open sets, like considering this open sets as G. So basically you can say that G is all open sets. Hence we can say that G is a subset. From that we can say that, wait a minute, G will be equal to G alpha, for some alpha will be equal to E, since E is open. So from there we can say that G alpha, that is E interior, is largest open set containing E. That is G is containing E interior. So we can say that G is a subset of E interior or contain E interior, and since E interior is open set, we get that G is E interior is the largest open set. Now to is precisely speaking, we can take a point X and we create a neighborhood of that X, and we consider that endo X a subset of G, and then this G belongs to the E interior. So we get that G, they take a point X belongs to E, take endo X a neighborhood of E, then and this neighborhood of endo X is a subset of E. We are naming this endo X as G, a subset of E. All right, and since for by previous explanations, this endo X contain other points other than X, for example Y. Since endo X is open set, it can contain it can contain many points, like for example Y belongs to endo X. If you consider the Y belongs to endo X, if the neighborhood if endo dash of Y is less than endo of X whenever do dash is less than 2. All right, so by this we can conclude that all these interior points of E is contained in an open set G, which is a subset of E interior. So we can conclude that from that we can conclude that E interior is the largest open set containing E. All right, now the last concept related to E interiors is that the complement of E interior is the closure of the complement of E. The last concept that we have here is that the complement of E interior is the closure of the complement of E. The complement of E interior, that is complement of E interior is the closure of E complement of E is the closure of E closure complement of E closure. All right, now to prove that, wait a minute. All right, so I have got the diagram for that. That is, E is a subset of X. Now we have this E closure. Maybe there could be another sets contained in X, so that's why I have drawn the line for E complement, or else you could not, you cannot have, you if you want draw a line for that, you will get X is equal to E closure if you do that. So for for explanation of this, I have just drawn this line, or else you could not, if you could have not drawn this, and there is no problem in that. Now we are considering a point X. A point X belongs to this E interior closure. All right, so that means that implies that X does not belong to E interior. That's it, right? If I consider a point X belongs to this complement, this is the E complement, and this is the E interior point of E. So that means E does not belong to that. From that we can write E does not belong to E. And we can from that we can say that X belongs to E complement. From that we can say that X belongs to E complement, right? X could be limit point of E complement closure. All right. For that, if a neighborhood, if you consider a neighbor endo X of X such that this endo X is a intersection with E complement will not be equal to phi. Means apart from that, this neighborhood, apart from the endo X, there is another point which lies in this neighborhood of X. When we intersect with this E complement, we are getting that it is not equal to phi. So we are considering that that could be Y. Y belongs to this. Y belongs to this. All right. If Y belongs to this, that implies Y belongs to this, and we are getting that Y belongs to the endo X. The neighborhood of Y belongs to the it follows from the previous theorem. All right. So from that we can say that endo X or this X belongs to E complement, or that implies X belongs to E complement closure. Since there is another point Y belongs to this neighborhood of X, from the definition of a limit points we get that X belongs to E complement closure. All right. So from that we get we have taken this part right over here, we get this part. So from there we can write E interior complement is a subset of E complement closure. All right, the first part I have proved. Now on the other hand, if you consider Y belonging to Y belongs to E complement, means if you are considering that Y belongs to E complement, this is a point Y belongs to E complement, then from that we can write that Y belongs to, from that we can conclude that from that we can get that if Y belongs to E closure complement, from that we can get Y does not belongs to E. Alright, and Y does not belongs to E, and Y belongs to E complement. Y belongs to E complement, that is what we take. Since Y belongs to E complement, we can write Y belongs to E complement closure, right? Since from that we can write Y belongs to E complement union E complement dash. All right, I can write it like this. E complement dash means if Y belongs to the closure of E complement, you get E complement union E complement closure. This is complement closure, right? So from that we can say that if Y does not belong to if Y belongs to E complement, then there is nothing proof Y is an interior point of E. If Y belongs to E complement closure, so that implies Y belongs, there is a neighborhood Y, endo Y exists, and from there we can say that the similar proof follows from that. Y is in limit point of Y is a limit point of Y is a limit point of E closure complement, and from that we can imply that E interior is a subset of E interior complement. Since Y is a subset, since Y is a subset of E complement, we get that Y is a subset of E interior complement. All right, so from there we get that E complement closure is a subset of E interior complement. From 1 and 2 we can imply from that E interior complement is a subset, is equal to E closure complement. This is what we get. All right, from this and this. we get this. All right, so you can follow your textbook for understanding it correctly. Now one more concept that is about the concept of interior E1. If there are two sets, E1 and E2 is a subset of Rn, then we can write interior of E1 intersection of interior of E2. And also if you take interior of E1 union interior of E2 is a subset of E1 interior of E1 union interior of E2. You can follow from the textbook. Thanks for watching the video. If you like my content, please subscribe and please like my video and share with others. Thank you very much for watching the video.